Welcome to the Ontology Summit 2026. Today is the 6th of May, 2026, and we are continuing our interoperability track. And I will now pass it over to our chair for this session, Todd, who will introduce our distinguished speaker. Todd.
Thank you, Kenneth. Welcome, everybody. Hope you're having fun out there. We're certainly going to have some fun shortly when Michael starts giving his presentation on the FIBO journey, an ontology for financial interoperability. If you've ever had to do anything in finance, you know it can be very confusing very quickly, and you want to escape as soon as possible. So Mike is probably best known as the originator of FIBO, the Financial Industry Business Ontology, that was developed to aid financial services in their, shall we say, terminological confusion. Michael is also the technical director of the Object Management Group and the board. He's on the board of the Ontolog Forum itself. So he's going to give us a description of the history and the origins of FIBO and the thinking behind the original conceptual semantic repository, and then bring us up to date with how FIBO is working with or as part of OMG, the Object Management Group. So Michael, it's all yours. Let's have some fun.
Thank you, Todd. Let me just share my screen. And yes, it's been quite a journey. I'm just going to put away little bits of Zoom so I can actually see my own screen. So you should now be seeing a full screen thing and no funny Microsoft nonsense. You're seeing all that?
Yes, looks great.
Put various badges around the place, which will be explained as we go. So yeah, I'm actually the director of Hypercube Limited, independent consultants. As part of that, I do serve as the technical director of the Object Management Group, responsible for the standards process. Before that, I worked for something called the Enterprise Data Management Council, or EDM Council, where I developed FIBO. And in a strange, curious circularity, the Object Management Group is now part of what's now been renamed the EDM Association. It used to be the EDM Council. So I'm not representing any of those things here. I'm describing the journey, how we got here, warts and all, because there are lessons to learn about which kinds of ontology do what. So I'll start at the very beginning. The motivations, why we felt we needed such a thing, how we went about trying to figure out how to represent concepts in finance, how to meet the need for clarifying the meanings of, what's a bond, what's an equity, what's a, preference share versus preferred share, are they the same or different, all those kind of questions. And we then brought that to the Object Management Group for standardization, and that became more of a semantic web OWL type of implementation. Some interesting lessons and back and forth on that. I'll touch on how we eventually ended up characterizing different kinds of ontology and what lessons we learned. And right at the end, just as a quick flashby, will be having got this kind of ontology, what are the different ways it can be used in interoperability, reporting, transparency, even semantic tech types of application and so on, and what that means for us in terms of how you characterize the right kind of ontology for any particular job. So we start at the beginning, right back in 2008. Although this is still the case, and it is always the case, you've got a bunch of financial institutions. They all have positions with each other in various things, be they swaps, forwards, loans, bonds, and so on. Each one could be a counterparty to another, and therefore owes different money in different currencies and different tenor, in other words, how long debt is out for and so on. So they've all got these exposures to each other, which is great, until a couple of them maybe start to look a little bit wobbly, as happened towards the beginning of 2008 and continue to happen. As they start to wobble a bit, then each other institution needs to know, oh, what's my exposure to that one? Because if that one goes pop, I'm suddenly left holding the other end of this debt position, but also the other end of that debt position. And do they owe me and do I owe them? And where did the money go? So in order to understand those exposures, what was interesting is when that financial crisis happened, and incidentally, Mike Atkin and I were walking along Wall Street one happy Friday in September, showing people this new idea we had of doing financial industry semantics and having this new thing, which was yet to be called FIBO. I think we just named it about then. And each place we went into in Wall Street had a longer story about bad things that were happening. And by the time we got to the end of Wall Street, the thing had gone pop. I promise we didn't touch anything. But when people then had these exposures, they had all the data they could possibly need. But unless you could link that to meaning, they didn't immediately know what their exposures were. It still took them weeks to go from having the data to having the knowledge of what exactly is our position now. So in order to solve that problem, you got all this data. These are just random formats, just as images. You got some stuff in some class model format. You got stuff in XML, XML SPY, whatever. And what tends to happen is that each time you get a new feed or a new piece of data, you get somebody technical in who understands XML or understands UML, and they get a great big spreadsheet and they map everything to everything else. Do they even know if they're mapping first interest accrual date here to issue date over there? Does it mean the same thing? Once they've made that mapping, do you even know whether they made the right mapping or not and what it means? So all these point-to-point mappings not only inefficient, but often wrong and always unauditable. So what you needed was some common repository of shared meanings, what we started to call very tentatively an ontology, without wanting to frighten the horses, to the extent that the first time somebody introduced us, they called it oncology. So we've come a long way since then. We haven't cured cancer, I'm afraid to say, but we needed not only a common point from an efficiency point of view, so each new feed or data model or application or whatever that you're integrating would link to the same set of shared business meanings, but also crucially, one, their business meanings, and two, because you have them as a common resource, you can audit at any point what somebody mapped this data element to or that data element to. If this one mapped first interest accrual date, and this is one of my favorite ones, and that one mapped issue date, and they're often the same date, but do they mean the same thing? If you find they were wrong, you can fix it because you have this common thing. So what we needed, very simply, in order to have shared business meaning, it's the business that has to own that meaning. Everything you model has to be validated by business, not the techies, not the person who wrote this schema or that UML model or whatever. And in order for business to validate things, you have to express it with logical formalism. So everything is completely unambiguous, but also presentable to those business people in terms of simple boxes and lines and telling what the box means, what the line means. We've even got odd little lines here for when one box of things is mutually exclusive with another. All the logic, which those of you familiar with OWL or description logic or even common logic and first order logic will know that you've got concepts like mutually exclusive and so on, which are simple pieces of logic, but we want to be able to present them to a business audience. So how do we do that? Well, I started right at the beginning. Let's look at what something is. Let's look at a formal definition of a thing. So we started with some possible classes of things. You've got commodities, entitlements, financial instruments. A little bit random this is straight out of some data model turned into OWL. Is it really an ontology? If you take a logical data model and turn it into OWL, do you have an ontology? No, you have a logical data model in OWL because it's the same model, just in a different formalism. So what do we do to figure out what things really mean? So I went right back. So this is one of the first things I did, went right back to a written definition from a published standard. I think this is the one it's probably in both CFI, ISO 19312 and ISO 20022. An equity is a financial instrument setting out a number of terms which define rights and benefits to the holder in relation to the holding a portion of the equity within the issuing company. Nice, clear, clean definition. Now, this is the first lesson we'll pick up later, where you've got written definitions and then you have an ontology. They better be saying the same thing. If the definition is clear, like this one is, and has specific pieces in it, what is it? It's a financial instrument, is a financial instrument. What does it do? It sets out terms. What are those terms? Terms which define rights and benefits. To whom? To the holder. What's the holder? Something in a role. In relation to their holding. Of what? Some equity. What's the equity? It's the equity of some entity, the issuing company. Nice, clean, clear definition, easily unpacked into particular pieces. it's a kind of financial instrument. It has rights defined in instrument terms. Those terms are defined in relation to equity as a thing. So now you've got a thing that's equity, a thing that's instrument terms, a thing that's an equity security, and so on. So first thing I did, and again, just using the simple logic of OWL, is popped it into an OWL model with a somewhat better visualization than some of the others. This is, again, very early, this one. You'll probably recognize it all in Top Grade Composer. I've just taken that same thing I just put on a slide. An equity instrument is a financial instrument. It has terms, equity holdings terms, which are a kind of holding term, which are a kind of instrument term. Everything links back to a kind of thing, and it sets out in simple relationships of generalization and properties linking one thing to another, exactly what was said in that written definition. So could we do that for everything? Now we can break it down. Now, if you started at this point, you go and look at the Ontology 101, the pizza, everything is a thing, pizza topping is a thing, pizza base is a thing. Well, that's not going to help you disambiguate very much. You want to isolate the common terms. So you've got accounting terms that apply equally to equity, debt, cash flow. You've got places, you've got legal. So we needed some better partitioning. We needed something more conceptual. Now, at this point, we looked at a number of frameworks. We looked at SPRL. We looked at Ronald Stamper's Norma thing. We looked at Semantic Media Wiki. Eventually, we ended up with OWL, which, for reasons we'll come to, is not the obvious language for defining a conceptual ontology, except there aren't any others. And we needed tool support. And at that point, there wasn't even really many tools. There is now Cameo Concept Modeler, for example, but back then there wasn't. So I wanted something with some tool support just to be able to present these diagrams that we said we'd need for the subject matter experts. And we could explain the basic, simple stuff. And I know there's higher orders of logic people are itching to tell us about, but we started with simple description logic. Everything is based on triples, subject, verb, object. They can be explained in reasonably simple terms to the business domain experts. So we set out to develop a concept ontology using those simple pieces of underlying logic, not to provide OWL reasoning or semantic querying or sparkle this or sparkle that, but simply to provide a visual representation of the set theoretic nature of this is a class of thing, these are the properties that define it, and so on. And the aim of this was, for years people had arguments about terms in message standards. We got various XML standards in finance like FIX and FPML and MDDL, which is gone now, and so on. And people would argue about terms, but then Mike Atkin was in a room with a bunch of them and said, well, what if we're not going to think about the terms, but the concepts, without worrying about what words, different people can use different words, but it's the concepts that matter. And then the argument suddenly stopped because, everybody realized that even when they're using different words or different data elements or column headings or whatever they're using, they know what the concepts are. They know what an interest rate is. They know what an issuer is, and so on. So we set out to develop what later got named FIBO. It was originally a semantic repository. We took as input all the knowledge that had already been figured out in the worlds of particularly ISO 20822, also MDDL, FIX, and so on. Don't know why we missed FIX there. We drafted, using that kind of boxes and line format, we drafted a kind of initial straw man of each thing, that equity thing that I showed you, for example. Presented that to subject matter experts, recruited experts for each topic based on what we were doing that week or that month. Presented it in boxes and lines, but also in spreadsheets, because human beings come in many flavors, and each of them thinks that the only way a mind is the way their mind works. Some people think in words and think that all thoughts are in words. Some people think visually, some people think viscerally, and so on, or audially. So we wanted to at least have the boxes and lines visually, but also the same information presented in spreadsheet format for those who are more comfortable with that. Now, underlying all that, we were using the underlying constructs of OWL. So applying a theory of meaning to that, we used an early version, which has now been published in a more mature and complete version of a standard from the object management group called the Ontology Definition Meta Model. So this was our first dealing with the OMG and this stuff. That meant that we could use tools in the UML modeling language, UML, Unified Modeling Language, creating a subset of UML and ODM constructs that we could use for readability, applying high-level concepts like archetypes for contract and location and so on, and eventually being able to express the thing in RDF and OWL, although initially we're using the OWL constructs visually without trying to create any RDF triples, and certainly without trying to create something you would run a reasoner on, because this is a conceptual model. So by definition, it's computationally independent, and that means being independent of any reasoning or other considerations. We're simply trying to capture the meanings of things. We weren't creating a semantic web application. We were capturing the business meanings that had been missing from all these other standards that were out there, the very successful standards that clearly captured real world knowledge, but not in a way you could express it unambiguously as meaning. To lock it all together, we used the top layer and only the top layer of John Sower's knowledge representation, KR lattice. And John, I believe you're on the call. This has been really helpful for us right from the beginning. We didn't use the rest of the lattice, but we used the top layer. So it was maybe misleading that we still called it lattice, because these three partitions are really easy to explain and justify to any group of business domain experts, often more easily than trying to explain it to some of the IT folks. So everything is either continuant or recurrent. That's your basic endurant or perdurant, as some languages call it. Concrete and abstract, we didn't use so much. There's the potential to expand that. And the other one we made a lot of mileage out of was the Peircean independent, relative, and mediating. So a thing in itself, a thing in some role, and the context in which it has that role. And we had the relationships for that applied actually to the thing itself, because you can sometimes have relative things relative to other relative things. Anyway, that partitioning allowed us to start providing clean top-down views. So we're no longer that pizza, base is a thing, topping is a thing. We could say, well, this kind of thing is a contract, and that kind of thing is a legal person, and that kind of thing is, and then you can specialize it. Every financial instrument is a kind of contract, the terms are contractual terms, and so on. So the first thing we did with all that, using this underlying early version of this ontology definition meta model, is I provided a bunch of views spat out from the UML tool. We're using the Sparks Enterprise Architect at the time. I had 3 levels of complexity for the graphics plus the spreadsheet to cover those 2 different modalities that people have. So a simple view, one that adds certain data type properties and actually other properties that we decided were simple enough that they should go in the box, and one with, I'll show you because it's easier. Here's a small corner of the equities model. So you've got convertible shares, convertible preferences shares, participating preferences shares, convertible participating. You've got intersections here. You've got multiple inheritance, of course. We show when things are mutually exclusive. We have blue lines for the relationships. So a preference share has a coupon. We introduced a few little logical funny things here which aren't part of OWL. And different colors based on these archetypes for when something is a contract term set, a coupon or dividend. I can't remember what the archetype of that is, and so on. Simple boxes and lines there for the simplest view for subject matter expert reviews, and then add more information on things like monetary amounts, dates, and so on. Things that have simple information kinds, mostly data type properties, but some of them selection lists and so on. So a little bit data driven, not fully conceptual as I'd understand it now, but trying to tease out in business terms how the business understands the meanings of what is an ordinary dividend, what terms apply to that ordinary dividend, how is that different from the preferred terms, and so on. What's the maturity date? All these things having labels and meanings and names and so on. And then the third view adds the relationships between the relationships. So the senior to relationship for a participating preference share being senior to a preference share specializes the relationship where any preference share can be senior to another class of preference share, and so on. There's a lot of others. So we got generalization hierarchies for properties and classes. We did not put properties. Some of these little switch icons, borrowed more or less directly from XML SPI, are intended to be either unions or restrictions on unions, but we didn't bring that yet. We were hoping when we eventually encountered some real OWL experts, they would help us to tighten up some of the logic. So we had lots and lots of sub-properties, mainly because each of those sub-properties often has an industry definition and a term and so on, and a meaning, even if you might use a restriction in a more conventional ontology. And we'll come to that a little bit in a bit later as to how that pans out. So that's our simple view. And then the same thing in spreadsheet. And I haven't mentioned this very often, but the spreadsheet, the structure of the spreadsheet precisely reflects the simple subset of description logic terms that we use. Something is a something, it has a related thing, it has a relationship fact. There you are. Is we use English names for things which any L expert or DL expert should recognize. Relationship fact is simply object property. Parent is simply generalization. Disjoint is simply mutually exclusive. We didn't want to try and educate the domain experts in our language. We wanted to put it in their language, and then everything has a term, a definition, synonyms, what type it is, if that applies, what things it relates to, and so on. And some business justification. There's other columns with term origin, definition origin, which later became meta model elements in the object manager group standardization of this. So what you have is simple boxes and lines. What does it mean to be an organization, a formal organization, a legal person, a human being? Notice that later on we can intersect. Some human beings are also legal persons. Some organizations are also legal persons. But we separate out everything to begin with. And crucially, you need to be able to have multiple inheritance here, which rules out some ontology frameworks. Things like being a contractually capable entity, that's the LEI, Legal Entity Identifier project, defines all the things that could be that. So that's the simple, here's another example, one that got into all that trouble as we were walking along Wall Street, the credit default swap. Very small subset of what's in that. But because we're using UML tool, we can produce several diagrams off the same model, some cleaner than others. See, this one doesn't have the relationships between the relationships. It doesn't have all the very detailed terms for contingent delivery and transaction settlement. There's lots and lots of terms for all of those. So we can isolate out subsets of the stuff presented to the SMEs, and they can say, oh, yes, Mike, but actually this credit protection transaction actually relates to this thing, not that thing. So we present the straw man and we tighten it up. And we use some iconography for things like parties in roles, like buyers and sellers and so on. But mostly we get boxes because then we could add simple types into the second partition of those boxes using UML when we needed to have a more complete view. So that was we had many years of doing subject matter expert reviews, some of it not really complete, some of it quite mature. And then we went to standardize this. We came to the object management group. Now, in order to talk about the standard, I'll start very quickly first with just mentioning, people often say, oh, you know, when you're doing an ontology, you've got to have competency questions, you've got to have use cases, you know. Well, to have a use case is to be an application. If you're doing a conceptual model, you're trying to lock down what things mean. It's computationally independent. It lives at the same level as a requirements catalog or a business process model or anything like that. That's a model of the business world, the business reality. However, we were helped by the fact that in all the terms we started from, when we went out and, you know, we created these straw man initial views of things to present to the SMEs who could correct and refine it and explain more complex things like credit default swaps and so on. A lot of the work had already been done on what terms are needed that we needed to define the semantics of, because all these standards bodies, ISO 20022, FIX, FPML, MDDL, which is defunct now, XBRL, which is definitely not defunct, very important spec. Those were all built by communities of experts over years using all their own use cases. We didn't need to come up with all of those use cases. In fact, we'll never find them all. What we did know is if something exists as an element somewhere in an FPML schema or a fixed schema, then we better define what the concept is. We know that concept is needed in finance. We don't need to go back to the use case to find it. And so you've got additional use cases for integration and reporting. And a subset of what you can do with some of these concepts is if you derive individuals in a knowledge graph, you can do inference processing, which nobody was asking for, by the way. What people were asking for was this common meaning for integration and reporting and so on. And so we got various ways FIBO can be used now. Maybe I should bring this to the end, actually. We'll come back to it. That FIBO has some roles in application ontologies, conceptual data ontologies, concept ontology. It's, as you'll see, a little bit of everything and needs to be adapted to each of these things. But these are all the broader use cases that FIBO was developed for. So we came into the standards process. We had a bunch of folks build a very complex infrastructure, which is still going at the EDM Council now, EDM Association, using Jenkins and GitHub and Jira and so on, to formalize the way in which we develop and update the RDF-OWL schemas. In fact, the first thing we did was they chased me up a mountain and made me not come down again until I'd completed the semantic repository in a clean enough way that somebody could run an automatic thing that turned it into RDF-OWL triples. There was a bit of magical thinking here, because some people sort of took the view that if it wasn't in RDF triples, it wasn't an ontology. And other people seem to have this magical idea that if you can reason over something, then it's meaningful. Therefore, if you can't reason over something, it's not meaningful and it's not an ontology. So there was an awful lot of not an ontology going on about all that stuff I've just described, which is capturing real business meanings. Apparently, according to the sort of semantic web tradition, that was all, quote, not an ontology. Now, as you know, if you can run a reason over something that doesn't make it meaningful, it tells you that it's not meaningful, which is good. It's a good quality step. So we're trying now to have FIBO as a semantic web compliant kind of ontology, while also hoping it can still act as this kind of Rosetta Stone that we originally had it as common business meaning. So this is a slide produced by others at the time to describe the overall process. So where do we go with that? We had a great process. There's more complex views I'll spare you. And again, this process is still running, and at the mechanical level, a very, very good process for managing, I would say, any OWL-based ontology. There's a repository, it's constantly updated, released every quarter. It's now maintained by the EDM Association, uses the best of Jira and Jenkins and GitHub and all the rest of it for automating the production of new and updated RDF-OWL triples for the ontology. Now, that then, we had all the original stuff we have for contracts like securities, derivatives, loans. We separated out time-sensitive stuff like pricing and yields and debt analytics and so on, and processed things like issuance and corporate actions. The core of it all in the original semantics repository, I had the upper ontology that I mentioned, that KR lattice, a set of high-level abstractions, including archetypes and so on for contract and geography. And in fact, in the tool I had about 10 or 15 palettes, each with about 20 or so classes and properties that were archetypal. So you could pull up a legal palette, you could pull up a geopolitical palette or a geophysical palette, mathematical palette, an accounting palette, and so on, each with common foundational terms, most of which are more abstract than anything specific to finance, because everything in finance, like everything anywhere really, specializes something else. A securities exchange, for example, is a kind of marketplace, just like a department store concession or a municipal marketplace or something like that. And so to define and lock in the real world meanings, we had these abstractions that were way beyond what you could possibly need for finance. And then we specialized into financial concepts like common business and commerce terms like interest rates and accrual and so on, and stuff around indices and business entities, which again could go beyond finance. So that was the overall packaging, and a lot of that's still there. We took off the top here for the standardization activity. Nobody wanted to see an upper ontology. The good news is, in place of the upper ontology, particularly the independent relative mediating partition, the OWL FIBO, the actual standardized FIBO, has repeatable, well-defined patterns. So they've basically replaced top-level ontology partitioning with OWL ontology design patterns. So that stuff's not lost. It's just no longer in an upper ontology. And in so doing, they also removed quite a lot of the process stuff, the ontology of occurrence, was considered too conceptual. In fact, the conceptual stuff was actually handed back to me, so my company and my colleagues and that. So what we left with is the contract ontologies and pricing analytics and stuff, and work has continued. This was 10, 12 years ago. Work continued since then on those as our ontologies. So what we started to see, and some folks in the community were starting to focus on, was there's these two ontological traditions. And I think that's a lot clearer now than it was at the time. I think more people here are familiar with this distinction now than perhaps were before. There's the implied ontology world. That's the folks that go to FOIS and IAOA and many of the folks on these calls. We think about the science of meaning. We think about how to express meaning in formal logic, presenting the language of the business with formal grounding in legal, accounting, and so on terms, versus a semantic web where you've got applications. They're use case driven, perhaps richer internal logic, more use of restrictions perhaps, although you can use those in both. But there's also a focus on data, and being applications, they're optimized. If you take the stuff that I originally expressed using the constructs of OWL and try and put it in a reasoner, it will probably fall over or keep churning all night, because to get the meaning right, you've got a lot more abstractions that you really don't need in an application. So these two traditions, with FIBO trying to straddle the two, and I think this is where we started to realize that we need more principled understanding of how these things differ. Now, I haven't got time to go into this bit in detail, but I just want to show you what the question is without trying to necessarily convince you the answers. So when you look at a semantic web ontology, and if you reverse engineer it into a tool like this, which is Cameo Concept Modeler or any other kind of visual tool, you'll see that you have properties with no domain and range, which, because this is UML-based tooling, you can't have arrows that are floating about. So they have a domain and range of thing, OWL thing, of course. So you have properties here. If they've got no domain and range, then really the only thing distinguishing them is the words they happen to have on the end of the line. There's no real semantics to that. And then some of these, you can see a subsetted like is to and is from. So what's going on here? How can we talk about meaning when you have properties with no domain and range? And that's not just in the FIBO world. Here's one that came out of an earlier ontology summit way back when we did some interesting workshopping. And this is using another tool from what was then Sandpiper, now Thematics, another ODM-based tool called Visual Ontology Modeler, or VOM. So I pulled in a very nice ontology that Mike Dean, some of you may remember the late Mike Dean, created as part of this workshop. And again, when I pulled it in and looked at it in this visual tool, because I'm a visual person, there's lots of properties with no domain and range, and then lots of restrictions that apply those. So I asked the OWL people, what's going on here? Because to me, I'm more of a cognitive science kind of person, more of an engineer. To me, meaning is how we present to the business folks. You've got a class of thing, you've got the properties that distinguish it, you've got the duck typing thing, is this a duck? Is this a duck is a waterfowl? Is a bird? Is a vertebrate? And so on. You have these simple ways of defining what things are. And none of that involves having nameless boxes. And certainly I would never present to a business domain expert something with nameless boxes, let alone properties that have nothing about them that grounds their meaning. Where's the meaning coming from? Well, the answer was, I finally had explained to me, who was explained to me? Fabian Neuhaus explained it to me, that what's happening here is that in the semantic web tradition, the OWL tradition, you're looking at meaning emerging from the graph as a whole, rather than grounding the meanings of individual properties and classes and building it up. At least where the properties are concerned, it's the use of that property in these different restrictions that defines its meaning, rather than the other way around. It's a kind of reversal. So I've tried to characterize this a little bit, that the way it was explained to me is you have, say, a relationship between things in the world. Here's a person, here's a bank where they work, here's a university they went to, here's somebody that taught them, here's an idea they had, whatever. There's a network of things in the world, and you have a corresponding network of elements in the graph. So the graph as a whole corresponds, if it's got enough detail, it can only match one set of things in the world. When you run a reasoner, you close that world and you check it for consistency, and you say, right, yeah, this is like having a map. If you have a map with enough towns and cities on it, if you just got two blobs, you don't know whether one of them's Dallas and one of them's Austin, or one of them's Liverpool and one of them's Bristol. But if you have enough other blobs, enough other pieces of the map, you can eventually disambiguate what that's a map of. Very much a contrast to what my instinctive thinking had been, the foundational semantics, where you have, like the electrical earth symbol, you have a grounding. This term is grounded in meaning independently of this network, such that every other term is defined in terms of its relations to it. This one's also grounded. Then the other terms all have their meanings in relation to a minimal number of grounded terms. And ideally, that's why we use top-level ontologies for a conceptual model, is that's where we ground the meanings in as few as possible concepts that everything else is defined in relation to. So those two traditions exist side by side. Neither of them is right or wrong. The foundational lends itself to conceptual modeling because you have deep classification hierarchy, very big disambiguation. The moment you walk into a bank, I've done this again from the bottom up in a big bank in Canada. Walk in, look at their model, define two different loan classes, and immediately I needed even more superstructure than FIBO had to capture the abstractions of which those different things were a specialization down at the bottom here. Whereas a semantic web application, you don't want all that slowing down the reasoner. You take an individual use case, you provide a small, self-contained, internally consistent model that you can reason over for that purpose. And one thing you don't want to do is try and use that semantic web style of correspondence semantics in a setting where you're trying to define common meaning and disambiguate concepts, because disambiguation is just a much more complex thing. So what this means is, well, even within the world of ontologies, let alone UML models or anything else, it helps to understand that there's a distinction between what formalism is. It first order logic? Is it object orientation, like class notation? Is it a state machine? Versus what's it about? That just having something in UML doesn't make it necessarily a data model, and having something in OWL doesn't necessarily make it an ontology. It depends on whether the subject matter is data or real things or something else, and how you're using it and what your abstractions are. These are all quite orthogonal concerns of any kind of model. When you introduce the data dimension, you're introducing data as a thing. I won't spend time on this. This is Jim Logan's slide, by the way. Thanks, Jim. That you distinguish between that which is a set of towers in the world, such as the Eiffel Tower, versus that which is a set of information constructs, such as database schema elements or whatever. So a bunch of us got together to try and figure out, this is the origin of, you may have heard me mention the semantic shed. A group of us met up in a shed in Wales and looked at, well, what's going on? How have we gone from having an ontology that was capturing business meanings in a form that subject matter experts could understand with full disambiguation and so on, to the semantic web tradition, which is what we've ended up standardizing through the standards process, through a really good, excellent physical process of managing our schemas, but with good metadata and definitions and really top range quality checks for a kind of ontology that doesn't have that semantic grounding anymore. It's not wrong, it's just different. So we kicked this around, and one thing we came up with was we were looking at a paper by McCusker, Luciano, and McGuinness, where they were quoting another paper from Smith et al. On the three-layer system, things in the world, our ideas of things in the world, and the representation of those, and realized that there's a distinction between an ontology of actual things, actual processes, actual people, versus our conceptualizations of those and the data elements that concretize those. So we need to have, we didn't necessarily need all three right away, but we needed to, that helps us make the distinction. It goes back to basic engineering again, between a conceptual and a logical and a physical model, that the logical model is more like what we were seeing as the semantic web style of ontology, the RDF-OWL type of ontology, which was delivered as the formal FIBO standards. that's sort of more like a logical model. What happened to our conceptual model? So we start to distinguish between an application ontology and a reference ontology and what they're for. Now, in order to understand that a little bit better, when we talk to SMEs about ontologies, we're not talking about any computational stuff. We're not talking about reasoners. We're talking about meaning. What does it mean to be this thing? What distinguishes that ordinary share from that preference share? What relationships do preference shares have with ordinary shares, and so on? And most of what we're talking about is what, in Searle terms, is social constructs. To be a bank is to have certain capacities, a legal capacity to take funds and disperse funds. Ownership and control. Ownership is a whole set of the right to hold, the right to dispose, etc. Specific rights and capacities, signatory capacity, for example. All of those are the real things in the world, and they're separate from the data. So the way we started thinking about this is, going right back to what I did at the beginning there. We had a model in description logic. We're using OWL as a kind of a way of describing that description logic. The description logic represents things in the world, or strictly our conceptualization of things in the world, to be philosophically correct. But to a simple business perspective, nothing to do with data. We're representing flowers and trees and fields and sun, actual things in description logic. You can serialize that in OWL. Now, that serialization still represents things in the world, but there's a little switch here, a little third rail. What happens if you suddenly create RDF instance data against those OWL constructs? If you have RDF individuals, well, you've effectively trodden on a third rail here. You've changed it from being a DL logic model of things to a DL logic model of data that happens to be an RDF. Now, it's not a very useful model, but the referent now, because you're creating instance data, your instances are data now, not the things. The previous are the things. You've trodden on the third rail. You've grounded this now in, this is now a model of data, but not a very good one, because there's an awful lot of stuff there you wouldn't want to see in data. What you really need is a conceptual data ontology in which you start to apply some design principles. You make typing decisions. Is something a float or an integer rather than it just being a number out there in the wild world? What kind of computational data types will you attach to it? Will it be a string? Will it be a date? And for some of those, as well as the data types, which you can do sensible RDF instance data with data type properties and so on. Because remember, a concept ontology shouldn't have data type properties because it's not data, it's things. So you make typing decisions, but also a whole bunch of things, including most of those social constructs. Instead of looking for the legal capacities that make something a bank, you look for data surrogates, such as a banking license, and say, if it has a banking license, that stands in for it having all those actual real world social constructs. Now, a lot of the data people struggle with the idea that those social constructs are the real world and the data is not. The data is not actually the concrete real thing. The data is actually the abstraction. So you got decisions to make. Now, this is still an ontology that's very conceptual in its structure, but now it has data types and data surrogates. And that will still be very different from the kind of ontology you would want to use to reason over, because it's still one that's going to really slow down your reasoner. But you could use it almost straight out of the box with instance data for an enterprise-wide knowledge graph. But for an application-specific reasoning application, you'd want to still extract and flatten out, get rid of the relative things, and use property chains to crunch them together. There's a whole lot of techniques there. But also in this same logical slice of the world, you can look at existing data models and reverse engineer those into data ontologies. Again, data, so our representations of a logical data model, right back where we started, including FIBO. So FIBO is in that nice middle ground. It's got a little too much for any one operational ontology and a little too little for full conceptual disambiguation, but it sits very well in that middle space and can be adapted up or down into either a conceptual or an operational ontology. So to firm this up, we try and create an ontology of ontologies. You have ontology, you you have a concept ontology or what we'll call a data ontology. Concept ontology, often called a reference ontology, so I'm distinguishing here between, using ontological terms here, the type of thing something is. It is a thing that is an ontology of concept versus how it's used. We're using something for reference. We often hear the word reference ontology. This is a reference ontology, but reference ontology really refers to its role. You're using it as a point of reference, a business meaning. So I'm separating the role from the nature. Likewise, with your data or application ontology, to have a use case is to be an application, of course. That's why our conceptual ontology shouldn't start with one use case. So applications can be all sorts. They could be for mapping, they could be for reasoning, there could be lots of individual reasoning use cases or querying or other use cases like that. And so, in fact, we can use FIBO or things like FIBO or different kinds of ontology in different scenarios. This is one we put together for the Bank of England some years ago. What if you could take all the green forms that they hand out to each bank and the banks all fill in and send back, and now they have to look at it and work out whether each bank put the same meaningful concept in the same box or a different box. And by the way, at least a third of those boxes are there to track places where people did put different things in the same box and the same things in different boxes, all flying about everywhere. What if you had a common ontology and you put your contract there, and your credit default swap there, and your interest rate swap there, sent it along as granular data? And the bank doesn't even need to send out new green forms every time they think of a new thing they want reports on. And they are green, by the way. They can just create a new query in a semantic querying language like Sparkle. But for that to work, you need a conceptual ontology here, and you need foundational semantics. Because if you're trying to use a reasoning ontology, it won't be granular enough to disambiguate all the concepts and capture all the kinds of data. And in many cases where a semantic web application would use a restriction, say if you've got something like, I don't know, derivative underlying. There's two kinds of underlying anyway. There's a reference underlying and a deliverable underlying, don't ask. Every different kind of derivative will have different underliers, and those will have their own definitions, their own terms, regulations about them, all sorts of reasons to surface them as a concept in your concept ontology, where our reasoning application would prefer to have just one simple property of underlying and then apply restrictions on that left, right, and center. So that's one thing. Another thing, again, talking to integration and interoperability here, is the R2RML stuff, the standard whereby you can turn legacy data sources in relational database format into a kind of industry-wide model. Again, now this one will be more of a logical ontology because it has to logically correspond to what kind of data elements there are, but still have foundational semantics because each of these database data sources has got different ways of arranging the same stuff and the same ways of arranging different stuff. So again, FIBO could be a subset of that for risk and compliance dashboards, reporting, and so on. And then you got mapping. Mapping's fun. There's not a one-to-one between any good ontology and any good database. The whole of this graph here, loan borrower postal code here, goes all the way from the loan to the borrower that's a party in role, that's the role played by an autonomous agent that has an address, the address has a postal code, maps to a data field that's simply loan borrower zip code, assuming you're the USA where postal codes are called zip codes. So you've got a whole graph mapped to an element. You've also got an element in the ontology mapped to a whole graph, so a whole set of terms in the source database. What's a medium-term note? It's a kind of debt, which is a kind of negotiable security. So it maps to a data model that might have a security class with a security type enumeration and an entry in that enumeration called medium-term note. So you got, three different values here mapping to one thing in the ontology. So that's where having the concept ontology lets you nail down these kinds of mappings in a cleaner way. And of course, because you're doing it in OWL, you could extract, and you don't want to use the whole thing, but you can extract a small subset like this. This is from some of David Newman's work at Wells Fargo. He's retired now, but was very influential in all this work. Take a derivatives contract like an interest rate swap, have a fixed float interest rate swap, and you can reason over it and do inference processing so you can surface new bits of information you didn't have before. There's actually a very minority use case. It so happens because it's what semantic web was designed for, everybody tends to think, oh, we're doing this now, therefore we're doing it for reasoning. Reasoning is one, or inference processing is one kind of application in which there can be some use for ontology. But again, you want to extract the right kind of ontology for that job. And one other thing we looked at, this was for a bank in Singapore, they showed us their big, horrible, untidy model and their business glossary, as they called it, with what were really lots of different and disparate concepts. And they had data models that they were trying to trace back to this business glossary. And how do you do that when different things in the glossary are pointing to different bits of the business concept stuff and different bits of the data model? It's all a bit of a squirrely, untidy mess. So by introducing not only an ontology, but the kind of ontology that has those simple partitions I showed you earlier on from John's lattice, which is roles and relationships of independent, relative, and mediating things. What's time? What's temporality? What's occurrent versus continuant? What's the difference between a record of a thing? So a borrower has a credit rating at the time they apply for a loan. They also have a credit rating now, and those are not the same thing. If you mix them up, you look up their credit rating now, that doesn't tell you what it was when you made the decision to advance on those funds, and vice versa. So teasing apart all those things, at the moment you have a whole lot of data silos with information held at a bank about a legal person, their customer ID, their first name, their customer ID again, their date of birth, their address line 1. We've all had the thing, you change your address and you tell the bank, and months later they're still sending stuff to the other address because it's coming from a different product that they didn't bother to cross-reference that. So by centralizing that, determining what's time sensitive and what's not, like loan application data, what's true of the entity all the time and can be updated when they move, what's history, what's roles and relationships, the information about that history, that drawdown date, that contact person for that particular product line versus the individual entity. So actually those top level partitions, which have no use in a semantic web application ontology and are not used in FIBO, although they are, as I mentioned, replaced by ontology design patterns, which do much the same job. But it's this top level concept ontology partitioning that actually lets you improve your partitioning of actual data, distinguishing record, time and future, contextual versus independent information, what's true of an entity always versus what's true of it in relation to that product or that product. Actually, the conceptual ontology can really help you clean up the data itself as well. So with 5 minutes left, I'm here for questions. That was the FIBO journey and some of the things we learned along the way.
Well, thank you, Michael. That's a lot of information to take in. I'm amazed that you can keep it straight. Can we ask you to be our financial advisor? Actually,
one thing about modeling things is like a cobbler's shoes. I don't wear them. Also have no money.
Okay, so nothing gets stuck to you, huh? One question popped in my mind going through this. What is English the de facto natural language that's used in finance?
Oh, okay, very good question. Actually, 2 questions really. I should say first, the chosen language for the semantics repository and later for FIBO is US English. And with some of the metadata we put together, we qualify that. Finance itself, I think it's more that a lot of terms that you need to track in any financial institution relate to US instruments because the role of the US dollar and the United States economy in relation to the rest of the world. So English ends up being a lot of it, but it's not like IT where programming languages are in English, whether you speak it or not. I think there's a lot of stuff goes on in other languages.
What language does that reconciliation bank in Switzerland use?
Oh gosh, yeah, probably English. Certainly when you do any international work anywhere in Europe, everybody uses not American English, by the way, but British and Commonwealth English. Even though Britain left the EU, they left their English behind, and everybody uses it. Including, of course, the Irish and the Maltese, who have it as a local language.
Yeah.
So,
Well, what language does that reconciliation bank in Switzerland use?
Well, the English language is English. It's I see a
Okay,
couple of
well,
questions,
I
and I
see
do have to
Gary
hop
and
off at the top of the hour. So,
okay,
Yeah,
Gary.
so I had a little trouble following where the interoperability issues were and the status of things. When you got into mapping, you were talking about things being a little bit squirrely.
mm,
And I'm not sure you had a specific example of how somebody else's vocabulary from a different jurisdiction would be harmonized to be made interoperable with your models and vice versa.
ooh,
And where I was wondering whether this is an active activity where somebody comes to you and say, "Hey,
mm,
I see that you have relevant things for me for funds, but we have different uh, ways of managing this. We're
right.
regulated in a different way.
Mm.
What do you do about that?"
Yeah, two things really. One is, yes, when you have different regulations and so on, that's why it's really important to isolate the concepts. But the other is when you have, as you mentioned, different terminologies and vocabularies, there's a whole bunch of slides that I didn't inflict upon you, where what we call pragmatics, of course, the meaning of a word in a given context maps to a different concept. And so you think of the vocabulary as a layer. If you could create a layer, there aren't really tools for this, but you create a layer around your ontology. So you have the ontology as the concepts. And then in different contexts, you should be able to switch out the different labels for what people call that thing in that context. And that's true whether it's data elements or vocabulary, human words. There's a lot to be done on that, I think, in terms of getting better vocabulary tools by grounding these in concept ontologies, which I'd love to see more of.
Do you find the
So,
idea of
John, you have
unpacking
about a
that
minute.
Nicola talked about and others have done relevant for your work? That is to say, you have to sort of elaborate your model into a deeper level until your model and a vocabulary are speaking the same language in terms of concepts?
Um, well, in terms of, I always keep the vocabulary decoupled as its own layer, but the really useful thing out of Nicola's work that's sort of implied in some of what I showed here is the notion of truth makers, that everything to do with the conceptual ontology is about what a real thing is, what are the truth makers that make something, or what makes you a bank, what makes you a legal entity or legal person, and so on. It's got nothing to do with data and everything to do with how you apply truth makers. And yeah, one day I'd love to understand and better apply Nicola's distinction between strong and weak truth makers and so on, because I think there's a lot of critical stuff there that when we got into this sort of semantic web, what some people call the pop ontology world, where if it isn't reasoned over, it isn't an ontology and so on, we kind of lost a lot of, well, what is an ontology and how do we apply the research from this community into that work, which is otherwise rather too sort of IT focused. And yeah, there's an awful lot of things we could still pick up on in that area. Unfortunately, I do have a call at one,
Michael,
but yes, I probably have a quick time for John's question
you have,
since his hands up, and then I'm going to have to hop.
John, go ahead.
Okay. One point that I'm very concerned about is the mapping to and from ordinary language, and what's
Mm,
now happening with the all the work with uh, the new technology based on the large language models is that we now have very clean and simple mappings from between ordinary English and first order logic, or even some examples of higher order logic. And
mm,
that mapping is very, very clean and simple. But there
mm,
is no clean and simple mapping between ordinary English and OWL. OWL is
mm,
just has this a horribly mistaken idea about that just destroyed Tim Berners-Lee's vision. So when you say
mm.
semantic web, I mean Tim Berners-Lee, much, much broader and much
Yes.
better, and it's much more consistent with what's happening now with all of the work in artificial intelligence. And
Mm,
all that means is that the owl is just such a teeny tiny subset. It's never going to
right.
go away. We must support it forever, but the movement must always be towards full first order logic
Mm,
and even better, the mapping to and from the semantic web. Not the semantic web, but the all the general the large language models. That's
mm,
the direction of the future, and I'm very concerned about developing software that is based on this rinky-dinky dead end instead of software that's moving towards the future.
I agree. I mean, I would see the
Well,
description
John,
logic as a core layer on which I'd love to be able to build up the other levels of logic in formal tooling. But even when you have tooling that provides business-facing views for even that subset of logic, vendors keep discontinuing it because nobody feels they're using it, because nobody's prioritizing conceptual modeling over and above doing techie modeling. But yeah, I'd love to see the layers of logic, the vocabulary layer, the pragmatics of separating out the term from the concept and all of that stuff. There's a huge amount of work to do and no tooling to do it in. So that's where we are.
Okay, well, that's a
well,
topic
Michael,
that
thank you. We
we'll
know
discuss
you have to
later,
go.
but-
John, please. Michael has to go. Unfortunately, he's given us a large amount of his time and a very entertaining presentation. So,
Sorry to
Michael,
have to
thank
cut
you
you
very
short.
much.
My pleasure. Thanks, everyone. Thanks for the questions. Man, with any more questions, and sorry I had to hop, but thanks.
Well, thank you, Michael.
Bye.
Bye-bye.